Hello students, welcome to the VTU EduSat program on Automata Theory and Computability. Let us continue with the lecture 9, which is on regular expressions. Okay, myself Girijamma HA, working as a professor in the Department of Computer Science and Engineering, RNSIT Bangalore. So for any of the queries you can mail me to the displayed mail ID. So let us continue with the today's sessions. So last class we have discussed about the regular expressions. So how to write the regular expressions for a given language. Okay. So and then building of a FSM for a regular expression. So here today's topics. So building a regular expression from an FSM. So this is the Kleene's theorem second part. So that will be proving, and the same thing we will discussing the examples also. Next is algorithm for FSM to regular expression, that is the heuristic method. That means, so for a given FSM, how to construct the regular expression using heuristic method. Next, so we will see some more examples on building up of a regular expression. Next will be a simple FSM with no simple RE. So why the author has prescribed this example is, here the FSM looks to be easy, but the regular expression will be complicated. We will solve this problem. Next, we will be proving the Kleene's theorem second part, that is for every finite state machine there is an equivalent regular expression. So first theorem we have proved it in the yesterday's, that is the previous lecture. So today we will be proving the second theorem. Next we will consider the algorithm to build the regular expression that describes the language accepted by the finite state machine from any FSM. Next we will see some of the examples on finding the regular expression for a given FSM. So let us start with simple example. So how to build a regular expression from an finite state machine. Okay. So for example, consider the finite state machine given below. So it is having three states. Q1 is the start state, Q2 and Q3. Q3 is the accepting state, and Q2 is having one self loop with B. So here you have to write the equivalent regular expression. So the easiest way is, so you can delete this state. Okay. So any state that has to be deleted will make it as a RIP state. Okay. So you can take this RIP state as Q2 and then delete it, and you should replace it with the equivalent expression as shown like this. See here, Q1 is the start state. Now Q3 will be the accepting state, same. So we have deleted Q2. So the equivalent expression will be A, B star, A. So directly you can write it like this. So the regular expression will be A, B star, A. But in applications we will not having very simple FSM like this, but all FSMs they will be complicated. So let us see how to go ahead with that. And we have an algorithm for converting the given FSM to regular expression. This is the heuristic method. So first let us see how we can go ahead with this. So it is FSM to regular expression heuristic. So the input is the finite state machine M. So first step is remove from M any unreachable states. So any unreachable states means from the start state, if any of the states are not reachable, or if you have the dead states also, so you can remove those states because they are of no use. And unreachable states, they are the states you cannot reach them, and dead states are the states, so you can reach them but there is no way to come out from them. So those two you can remove it in the first step. Next step is no accepting states, then return the regular expression phi. Okay. So we know that phi is the empty language. So this regular expression, it will be there when there are no accepting states. So this we have discussed it. So third step is, if the start state of M, it has incoming transitions into it, then create a new start state S. Why? Because so M is the start state and only it should have the outgoing transitions. There should not be incoming transitions. So if any of the finite state machine it is having the incoming transitions, or if it is having a loop with that, so what you should do is, so you should create another start state S with the epsilon transitions to the old start state. And similarly, so if there are more than one accepting state, okay, of the finite state machine, or one accepting state with outgoing transitions from it, then create a new accepting state. So in a similar way, how do we create a new start state? So here also, so sometimes in the finite state machines we will be having more than one accepting state. In that case, what we have to do is, so you have to create another accepting state, so with epsilon transitions from all the accepting states to the new accepting state. Okay. So this procedure we need to follow before converting the finite state machine to regular expression. Next, fifth step is, if the finite state machine has only one state means, then we will return the regular expression epsilon, because it accepts only the null string. Sixth step is, until only the start state and accepting state remain, so we have to repeat some steps. So what are all those steps is, first select some state rip of M. So like in the previous example we have removed Q2, so in a similar way, keeping the start state and the accepting state, all other intermediate states have to be removed. So when you select the some state as rip and when you remove it, so you should modify the transitions. Okay. So instead of state, we will replace the equivalent transition, whatever you do it, but the language accepted by the finite state machine, it should not be modified. Next, last step is, so return the regular expression that labels from the start state to the accepting state. Okay. So once you delete or remove all the states, so you will be left with start state and the accepting state with one regular expression on it. So that will be the final regular expression. We will consider one example for building a regular expression from the finite state machine. So let the finite state machine be as given below. Okay. So here you observe there are three states, 1, 2, 3, and state 1 is the start state as well as accepting states. Double circle means it indicates that it is also an accepting state, and here state 2, it is double circle means it indicates that it is also an accepting state. So next state 3 is there. So here, so what is the first step you have to perform is, so here since there are incoming arcs for the start state, you should create a new start state, and also there are two accepting states, so you should create a new accepting state. So first step what we will be doing is create a new start state and a new accepting state and link them to M. Okay. So when you observe here, there are no dead states or no unreachable states. Okay. All the states are reachable, hence we will not modify the FSM, just we will add a start state and new accepting state to the finite state machine. Okay. So when you do the first step, that is after adding the new start state and the accepting state, so your finite state machine looks like this. See here I have added the new start state 4 and with epsilon transitions to the old FSM, and then the new accepting state 5 with 1 and 2 earlier they were the accepting state. So with epsilon transitions you need to connect to state 5. Okay. So this is the modified finite state machine after step 1. Okay. So next, so keeping the starting state and the final state, you should remove all the intermediate states. Okay. So let us do it one by one. I will select the state 2 as the rip state. Okay. So I select the state 3 as the rip state. Okay. So, when you are going to select the state 3 as the RIP state, the equivalent regular expression for reaching from 2 to 1 is A star B. Okay. So, when you are deleting this state 3, so you should replace it with the equivalent expression A star B. So, that is what we have done here in the after removing the RIP state 3. Okay. So, now state 3 has been eliminated, and instead of it, so you have a transition from 2 to 1 with the label A star B. Okay. So, this is the FSM after removing the RIP state 3. So, next let us remove the state 2. Okay. So, we will first 3 we have removed it, next we will remove state 2, next we will remove the state 1. Okay. So, when you remove the state 2, so you observe here from 1 to 1, okay. So, there is a transition from 1 to 2. So, you can reach from state 1 to state 2 with the transition A, and with state 2 to 1 you can reach either through B or A star B. Okay. So, when you are removing this, so whatever the transition it is accepting from 1 to 1, so it should be there. So, here we will write a self loop, and then so we will write either AB union A followed by A star B. Okay. So, why this A is because from 1 to 2 we have A here. Okay. Again from 2 to 1, so you can reach A star B. So, for 1 to 1 we will write a self loop and then label with AB union A followed by A star B. And a similar way, so you can also, there is one more transition from 1 to 2 you can reach with A, and from 2 to 5 epsilon. Okay. So, if you concatenate A followed by epsilon, it will be A. Okay. So, that is why whenever you remove it from 1 to 5, so you can write the transition A. So, let us see how it has been modified. Okay. So, after removing the RIP state 2, so it has been modified as, so state 1 is having a self loop which contains AB union A followed by A star B, and we have a transition from 1 to 5 A. So, that is the modified FSM after removing the RIP state 2. Next, let us take the state 4 as state 1 as the RIP state. Okay. So, if you want to remove this state 1, so it has having a transition AB union A star B. Okay. So, followed with, so you can reach with to state 5 either A or epsilon. Okay. So, 4 1 to 5. So, you can, since here it is a self loop, star is there, so we need not write epsilon because this star indicates 0 or more number of times repetitions. So, directly you can write this only. So, final regular expression will be AB union A star B for that whole star followed by A or epsilon. Okay. So, let us see how it looks after removing the RIP state. Okay. So, only the start state and the accepting state 5 are there. The regular expression will be, so AB union A followed by A star B, which is of whole star because it was a self loop. So, whenever you are removing the self loop, so you should put the star here followed by either A or epsilon. So, the final RE is this one, keeping start state and the accepting state, all the intermediate states have been removed. Next, we will consider a very interesting problem the author describes everywhere. Okay. So, here in the module 1 we have seen this deterministic finite state machine where the state 3 is a final state when you have even A's and odd B's. Okay. So, this is the DFSM constructed to accept when the number of A's are even and number of B's in a string is odd. Okay. So, when you want odd A's and even B's, so you can make 2 as the final state or the accepting state, and whenever you want even number of A's and even number of B's, so you can make this state 1 as the accepting state, and whenever you want odd number of A's and odd number of B's to be accepted, so you can make state 4 as the accepting state. Okay. So, if you consider this finite state machine, it looks simple, but if you try to write the equivalent regular expression, it becomes complicated. Okay. So, let us see how to write the regular expression. So, before going to that regular expression, we will consider the Kleene's theorem part 2. So, what does it state is, for every FSM there is an equivalent regular expression. So, we know that, so regular expression, they are the ways to accept the regular languages. Okay. So, every regular language can be defined with a regular expression. So, we will prove this by construction. So, we will consider the finite state machine M, which is given with K, sigma, delta, S and A. When we construct a regular expression alpha such that the language accepted by this machine is equal to the language accepted by the regular expression alpha. So, let us see how to construct. Suppose in your FSM there are 2 transitions like this, A and B. If you observe, from the state 1 to state 1, both are going on the same side, then you can collapse and then you can write A union B. Okay. So, this is when they are in the same direction. Okay. So, when they are in the opposite direction, you cannot write like this. Union you cannot use, but you can use the concatenation. Okay. So, likewise similarly, if there are multiple transitions C1, C2, C3, etc. up to Cn transitions are there. So, you can delete all these transitions and replace with the equivalent transition with C1 union, C2 union, C3 up to Cn. Okay. So, this is collapsing the multiple transitions. Next, if any of the transitions are missing, add them without changing L of M by labeling all of the new transitions with the regular expression phi. Okay. So, we know that phi means empty language. Okay. So, whenever the transitions are not there, so if you replace it with phi, it will not harm any FSM. For example, if you consider this FSM, okay. So, here there is no self loop here, and 4 to 3 transition is missing, and you have the transition from 4 to 2, but 2 to 4 it is missing. So, what does the author says is, so accordingly, so you can add the transitions with labeled 5 like this. See, I have added the 5, 5 and 5, and similarly from 1 to 3 there is no direct regular expression, there is no transition. Okay. So, you can add with phi. So, phi, it will not harm the any language, the earlier whatever the FSM accepts. So, this also accepts the same language. Next afterwards, so what we will be doing is, so we will be selecting a state, rip and remove it and modify the transitions as shown below. Okay. So, we will be using this formula. So, for example, if you consider any states P and Q, once we remove rip, and how can we get M from P to Q? Okay. So, what for that we will use this formula. So, what does it formula is, R of P comma Q be the regular expression that labels the transition in M from P to Q. Okay. Then the new machine M dash will be removing the rip. So, R dash of P comma Q. Okay. So, for example, so R dash of P comma Q is R of P comma Q, that is from direct union R from P to the rip state and R rip comma rip star. So, because there will be a self loop, and then again the regular expression which is from RIP to the state Q. So, let us consider an example how we can write it. So, for example, the previous example, so let us take I want to delete the RIP state is state 2. Okay. So, there is I want to find the transition from R1 to 3. So, that is given by R dash of 1 comma 3. It is nothing but R1 to 3. This is from the directly whatever we are having. Since the transition from 1 to 3 was not there, so we have added it as 5. That will take it union R1 to 2. 1 to 2 is A and RIP to RIP, that is B. Actually, your self loop is missing, it is B. Okay. So, we will be writing here B star, and then from 2 to 3 we have A. So, A will be writing. So, this formula, so we can use it for any of the FSMs. Okay. So, from 1 to 3 if you are calculating, and state 2 is the intermediate state, whenever you want to remove it, so you can use the formula, that is R1 to 3 union 1 to 2, next R2 to 2 star for that, because it will be a self loop, and then 2 to 3, so which is A. Okay. So, it is 5 union AB star A. So, the answer will be AB star A. This is not the final regular expression, this is after ripping out state 2. That means, when you remove the state 2, so what will be the equivalent regular expression from 1 to 3? So, you can write it as AB star A. So, accordingly the previous theorem, so it is modified, and the algorithm, we have an algorithm to build the regular expression that describes the L of M from any FSM M. Okay. So, according to the Kleene's theorem, so there are two subroutines. First one is standardize. So, this standardize, so it will convert the given finite state machine to the required form. The second one is build regular expression. Build REGEX means it is build regular expression. So, what here we will be doing is we will be constructing the required regular expression from the modified machine. So, these two subroutines are used to find the regular expression from the any FSM. Okay. So, first one is standardized, second one is build regular expression. So, in standardized, so we will be converting the M to the required form, that is if there are any dead states, unreachable states, so all that will be removing it, and we will be adding the start state and the accepting state required, and then so these things will be doing in the standardized. Build regular expression will be collapsing the transitions and ripping out the states, keeping only the initial and the accepting state. So, we will build the regular expression. So, let us see what is standardize. So, what is standardize of M of FSM? Okay. So, here it states that first remove any unreachable states from M. Next, modify start state if required. Okay. So, that means it should modify the start state, means it should not have a self loop, or the start state it should not be a part of any loop, only the outgoing transition should be there. There should be no incoming transitions, okay, for the start state. In that case, you should modify the start state, and a similar way, so you should modify the accepting states. So, this is possible when there are more than one accepting state. Okay. When there are two accepting states, we will not do that one. 2 will keep it as a normal state, and will add the new accepting state with epsilon transitions to that. Okay. So, that we have seen it. And if there is more than one transition between the states P and Q, we will collapse them to single transition, that is the collapsing. And if there is no transition between P and Q, and P does not belongs to an accepting state and Q does not belongs to an start state, then we create a transition between P and Q labeled phi. Okay. Since phi does not harm the language it accepts, always whenever transition is not there, you can write the transition, you can write phi. So that is the standardized steps. Next, how to build the regular expression from the FSM. Suppose first step is, if M has finite state machine has no accepting states, then return the regular expression phi. If there are no regular expression, then it denotes the empty language, will return the regular expression phi. If M has only one accepting state, then return the regular expression epsilon. Okay. So since epsilon accepts the strings of null strings, okay, of 0 length, so you can return only one accepting state, means you can return epsilon. Third step is, until only the start state and the accepting state, so you can repeat these 3 steps. So what all these 3 steps is, select some state rip of M and then find the equivalent transition. Whenever you have selected some state as rip state, so you are removing it, so you should find the equivalent transitions. Like previously we have discussed, it is r dash of p comma q is given by r of p comma q union r of p comma rip dot r of rip comma rip star dot r of rip comma q. So using this formula, so you can find the equivalent transition, and then we'll remove the rip on the all transitions to it and out of it. Then return the regular expression that labels from start state to the accepting state. So let us see some examples and how to build the regular expression from FSM. So the same example which is given in the textbook, so I have taken. So we in the last when we discussed the algorithm, so we found the equivalent transition from 1 to 3. Let us find the equivalent RE what this FSM accepts. So the question here is how to build the regular expression from the FSM. Okay. So here start state is having only the outgoing transitions and only one accepting state is there, only it has the incoming, there are no outgoing of it. So no need to be modified state, start state and the accepting state. So directly you can remove the intermediate states, that is state 4 and state 2, and you can proceed it. Okay. So first step is, I have selected state 4 as the rip state. So when you are selecting the state 4 as rip state, so you should replace it with the equivalent transition. So from state 1 to 4 you have a transition B, and from 4 to 2 you have a transition B again. So B followed by B, directly you can place it to 1 to 2. So that's why I return 1 4 2 is B B. Okay. So after removing the rip state 4, so your FSM looks like this. So state 4 it has been removed. Now you have a direct transition BB, and then so this remains as it is. Okay. So now you can collapse these transitions. Since here BB is there, here A is there. Okay. So you can write A union BB. So after collapsing the multiple transitions from state 1 to 2, so you can write from 1 to 2 A union BB, and state 2 is having self loop with B transition, and from 2 to 3 it is A. Okay. So next we can select the state 2, only one state is remaining, 1 and 3 are the start and the accepting states. So remaining those, so the left out state is state 2, so which has to be removed. Okay. So in the next third step, rip state will be state 2. Okay. So what happens when you remove this? So you have from 1 to 2 transition A or BB, next you have a self loop with B star, next followed by A. So we'll write it the same thing as it is. So after removing the rip state 2, so you have the transition A union BB followed with B star A. So here only one start state and one accepting state. So this will be whatever the transition on that label, on that transition you have it, that will be your final RE. Okay. So this becomes the regular expression. So this is the problem which has been discussed in the textbook, but this solution is not given. Next we will take one more example, how to build the regular expression from the FSM. Okay. So this is looks like here there are 4 states. The starting state is also an accepting state, and if you observe here state S, there is no, you can reach the state but there is no way to come out. State S is the dead state. Okay. So as I said, if there are any unreachable states or the dead states, so you can remove them. So step 1, what we are doing is you remove the state S as it is a dead state. So after removing state S, so we have like this. So here state S has been removed and its transitions are also not necessary because no need of adding them. So you will be left with only P, Q, R. So now what we have to do is, since this is also an accepting state, we have to modify, we have to put one start state and one accepting state. So in step 2, we will be adding new start state T and new accepting state U. So after adding T and U, so your figure looks like this. Okay. So now your FSM is having new start state T and the accepting state U with epsilon transitions. Okay. So now, so you can select keeping T and U. So you should remove state Q, R and P. So let us do it one by one. So let me select the state Q as the RIP state. Okay. So if keep Q is connected only to state P, to no other states it is connected. So from P to Q and again coming back from Q to P, so you have only the transition 0, 1. Okay. So I have written here P, Q, P is 0, 1. So if you remove Q, so instead of it I can place a self loop here and I can write 0, 1, because this 0, 1 it can be repeated any number of times. So when it is repeated any number of times, so you can add a self loop. So this is the finite state machine after removing the RIP state Q. So we have written a transition, that is the self loop on P with labeled 0, 1. Okay. So now, so let us select the state R as the RIP state. Okay. So if you select state R as the RIP state, so here also you observe R is connected only to P, to no other states it is connected. From P to R you can reach with the transition 1, and from R to P you can go back with 0, that is 1, 0. So if you are removing state R on the P, you can write the self loop 1, 0. Already 0, 1 is there, so we will be writing with union. Okay. So after removing the RIP state R, so it is 0, 1 union 1, 0. Okay. So if you take out the state P also, you will be left, the final regular expression will be 0, 1 union 1, 0 whole star. So this is the final regular expression. So now let us move to a simple FSM with no simple regular expression. So previously I discussed this example. Okay. So to find the regular expression, it was a complicated. Here this state 3 is the final state and it contains even A's and odd B's. Okay. So let us proceed how to find the regular expression. Okay. So if you observe here, the solution is, the author has not given the solution, it is left as an exercise. This problem found for me very interesting, so I have solved this problem. So it is, the step 1 is, so there are no dead states, add the new start state S and the new accepting state A. Okay. So like author has described the algorithm, so he has, I have added the new start state S because the state 1 it is having the incoming transition and So, 3 was the accepting state which has the outgoing transitions. Okay. So, state S and state A are added. S is the start state and A is the accepting state with epsilon transitions. Okay. So, next you have to remove all the states 1, 2, 3, 4. So, let us proceed by one. Okay. So, first I will be selecting the RIP state as state 4. If you are removing the state 4, so there are many transitions out of it. Okay. So, I have not placed the 5 transition. So, the author has described in the algorithm. So, you can connect with 5. Since this is a very big regular expression, directly I have written it. Okay. So, if you observe here, if you are removing 4, okay, there are here 2 transitions, these 2 transition. So, 4 is connected to 2 and 3. Okay. So, if you observe, if you remove it, so always it should be replaced with the equivalent transition. Okay. So, if you observe here, from 2 to 4 and again 2, you can reach with the transition BB, that is 2, 4, 2, BB. And in a similar way, 3, 4, 3, you can reach with AA. And again from 2 to 4, you can reach with B, and from 4 to 3, you can reach with A. So, I have written here 2, 4, 3 as BA. So, what you can do is, instead of after removing this state 4, directly you can connect from 2 to 3 and you can write BA. And similarly, from 3 to 4, there is a transition A, and from 4 to 2, B. Okay. So, directly you can connect from 3 to 2 with the transition AB. So, these 4 transitions are to be modified in the finite state machine after removing the state 4. So, after removing the RIP state 4, okay, 4 it has been removed. So, 2 to 3 you have BA, and 3 to 2 you have AB, and here there is a self loop BB, and here there is a self loop AA. So, this is the modified FSM after removing the state 4. Next, so I am selecting state 2 as the RIP state. Okay. So, state 2 it has to be removed. Okay. So, state 2 is connected to state 1 and state 3. Okay. So, you have 1 to 1. Okay. So, that is 1 to 1 with the transition A, BB star and again A. And in a similar way, from 1 to 3 you have A followed with BB star and then BA. Okay. So, that is whatever the transitions are there, I have written here. Next, 3 to 1. Okay. So, from 3 to 2 you have AB, that is AB, and then BB star and again A. That is, this is from 3 to A. Again, 3 to 1. 3 to 3 you have AB, this is the AB transition followed with BB star, and again you can come back to state 3 with BA. So, whatever the transitions are there, I have written it. Next, so when I remove this state 2, so what I will do? So, directly from 3 to 1 I have B. Okay. So, along with the B, so you can write with the regular expression. So, 3 to 1 you can reach with AB, BB star A. Okay. So, you can write the regular expression RE2 as B union AB, BB star A. And in a similar way, from 1 to 3 already you have B transition. Along with that, so you can write A, BB star BA, that is A, BB star BA. So, directly you have this transition. Along with that, also you can reach with this transition, and here the self loops on 1 and 3 are to be modified. Okay. So, on the self loop 1 we are not having, so that you can write the regular expression as RE3, which is A, BB star A. But on the state 3 there is already we have a self loop AA. So we will be writing the regular expression RE4 which becomes AA union. So you can reach AB, BB star, then again come back with BA. Okay. So these are the regular expressions RE1, RE2, RE3 and RE4. So we will be taking it out. So next let us remove the state 2 and then write it. So after removing the state RIP state 2, so it has been modified like this. So we know here this is RE3, then this is RE1, RE2 and then RE4. Okay. So these are the regular expressions. So the same diagram I have redrawn it here. So it looks like this. Okay. So next we can select the state R3, the state 3 as the RIP state. Okay. So if you remove the state 3 as the RIP state, so you can connect from 1 to the accepting state through the regular expression RE1 and RE4 star. Okay. So if you are taking out this, so from RE1 to A, so you can connect RE1, RE4 star. And similarly here you have the regular expression RE3. Along with that you can write RE1, RE4 star followed with, again you can come back with RE2. So that's what I modified the regular expressions as RE5 and RE6 have written here. Okay. So this is from state 1 to A after removing the state 3, and this is RE6. RE6 is nothing but RE3 union RE1, RE4 star and RE2. Okay. So the final regular expression will be epsilon followed by RE star followed by RE5. So next state removed is state 1. Okay. So you will be having the start state S and the accepting state A with the regular expression RE6 whole star RE5. So you will be getting a very, now we will replace this RE6 with their values. So you will be getting a very big, very lengthy regular expression. But this problem is very interesting, as in each step we will be noticing how to replace it with the equivalent transition. This problem, it has not been solved in the textbook. So this problem found to be interesting. So final regular expression, when you replace the values of RE3, RE1, RE4, RE2 and RE1, RE2, so we will be getting such a big expression. Next, so one more problem is, so this is an assignment problem. So where you can try this problem. This is a problem number that is the example 5.3 from the Aligned Rich textbook. Okay. So this is also an exercise problem. Okay. It found to be very interesting. Okay. So just here you can leave bar 0, those are output symbols that you can leave. Only the input you can just take 0, 0, 0, 0 and then so with whatever its 0 is there that you can take, and 0, 1 and all you can leave. So start from here 0, 1, 2, 3, next 4, 5, 6. Okay. So if you try this problem, okay, so if you it will come after some 8, 9 steps. So the final regular expression will be this, such a big regular expression, and this is very interesting. How to proceed with that? Okay. So first, since there are outcoming arcs for the starting state and also it is an accepting state, add one start state and one accepting state. Okay. So next step, you should select this state as, that is state 1, it has to be removed. So you can remove this state, and then when you are removing it directly you can connect with this to this with 0, 0. But one thing you should remember, so you can, when you are removing this, so you can reach this state with the transition 0, 1. Okay. So when you are removing this transition, you should add true transitions. That is one direct transition from this state to the state 2 with 0, 0, and from this state to the state 1 like with 0 1. Okay. So, if you modify and remove state by state, first you remove this state and you take this state as the RIP state and remove it, and you take this state as the RIP state and remove and replace the equivalent expressions. Finally, you will be left with the regular expression this. So, I suggest students you please solve this problem and find the regular expression. It is an very interesting. So, let me summarize today what we have discussed. Okay. So, we have discussed the Kleene's theorem second part, and we have discussed the examples, that is how to build the regular expression from the given FSM. Okay. So, there are two methods to be followed. One is the heuristic method, another one is the algorithm, that is the Kleene's part second theorem. So, whichever is comfortable, so you can use it. Okay. So, no problem if you are using any method. One thing you remember, whenever you are removing the state, you should remember that the language accepted by the FSM should not be modified. Okay. So, it equivalent regular expressions on the transitions should be written it. So, like that if you solve it, no problem if you remove the transitions. Okay. So, this is about today's lecture, and if you have any queries, so you can mail me. So, the mail displayed is girija.kasal@gmail.com. Thank you all.